In my previous video, number 64 in this series, I found indications of noise in the input hybrid here. That is, of course, a general problem for all cross-correlation measurements. Could there be noise problems in the hybrids? Later in that video, which you might have seen, I found indications that the problem could have been something with the sound card, the UADC4, which doesn't behave the same way after reboots or restarts. It has several states with different properties with regard to correlated noise. To investigate those hybrids, I made this following experiment. The 1 watt oscillator, one of the hybrids, and the delay line, and the second hybrid, because they are not the same type, so I have to match the phase here. And then a resistor here, into which there is very small power. And then the signal here, which is nearly all the power, it's attenuated by about 1 decibel. And then the iron-free hybrid, which is noise-free, and the 2-channel receiver. And here is what I see after about 8.5 hours. So phase noise, 200 Hertz minus 173. Sorry, 200 Hertz there. Yes, 173. And 400 Hertz, 175 roughly. I will change the scales a little bit. 200 Hertz is this spur, and it comes, as we can see here, at 172.5. 400 Hertz is this one, and it's a little bit more uncertain, but I can say minus 177 if I take the noisy signal. 176.8 perhaps. Here is the amplitude noise. I use this ruler because the peak is not well visible. This is 400 Hertz, and it comes at minus 174.5. This is AM noise, 200 Hertz here. It comes at this peak, which is negative, and if I try to read it, it looks like 171.0. Here is the result from my previous video. Minus 170 is this line, and my findings now, 200 Hertz, minus 172.5 for the phase noise. 200 Hertz is here. 172.5 is here. It's within 1 dB and actually a little bit better. And the amplitude noise minus 171, it's here. And that's degraded by almost 3 decibels. 400 Hertz, this line here, phase noise minus 176.8. That is 76.8. It's here. It's half a dB better. Amplitude noise minus 174.5. That is here, and that is degraded by 3 decibels. Now, these differences are small, and this isn't really the way to study the hybrids. I could swap here and analyze the signal in this port and put the resistor here. These are the signal levels, 1 point a little bit. in the 4 channels. Now I'm looking at the output of the other hybrid, and as you see, the levels are lower. Taking the difference in the 4 channels gives me 15.18 decibels lower signal level now. It means the carrier is 15.2 dB weaker, but the noise that might be generated in the hybrids is not attenuated. It should add the same noise into both outputs. I am adjusting the gain of this 2-channel receiver by having attenuation or amplification here to always keep the level into Linrad constant. So the levels into the mixers are roughly as before. So I will take notes so I know what levels we have. After 2.5 hours, I see there is not much difference on the phase noise. It is very similar. But when I go for the amplitude noise, it is different significantly. Here is the amplitude noise again in an expanded scale. When I read off the screen, I see these values from 50 to 400 Hz, but I have to add 15.2 dB, or rather subtract to get a numerically bigger result. So this is what I observe as the amplitude noise from the 2 series connected hybrids. These points fall on a straight line here, it's like this, about 10 decibels below the values I have observed for the oscillator. So these hybrids are good enough, but the margin is not very large when it comes to AM noise. AM noise is down here, and I don't know at what point it will start to go as 1 over F. Probably it is about here. Now I have increased the length of this cable slightly. It wasn't accurately cut for this purpose. And now the signal levels are much lower. And when I subtract, I find again 15.2. So now the carrier is reduced by 30.4 dB, and also of course the noise from my oscillator, but remains thus the noise generated by the hybrids and possibly connectors and other stuff that's involved. And now the signal levels are much lower. And when I subtract, I find again 15.2. So now the carrier is reduced by 30.4 dB, and also of course the noise from my oscillator, but remains thus the noise generated by the hybrids and possibly connectors and other stuff that's involved. I haven't adjusted the gain of the 2 channels as I could have done, because the noise is strong enough to be very clearly visible here. This is the phase noise. And here is the amplitude noise. I see at 200 Hz minus 149. And when I add 30 dB, that becomes 179, which is here. So I can do this a little bit more accurately, but I have inserted the amplifiers in the 2 channels to restore the level into the sound card. And then I see this. There is no need for correlation anymore to see the noise up to about 200 Hz offset. And At 1 kilohertz I can see the noise here. The correlation gives me a correlation gain of just a couple of dB. It's 1 dB per division. This is amplitude noise. And here is phase noise and amplitude noise. And here is phase noise only, and it's the same. I can see the phase noise without correlation. And the imaginary part from correlation is down here, very far below. And I can see the phase noise almost at the DC. This is a very small range that isn't visible anymore because of the noise at 0. I mean, that peak comes at 700 Hertz because the carrier is at 700 Hertz. So I take down some numbers of this. These are the numbers I read, raw data and corrected for the 30.4 attenuation of the carrier. And the screen looks like this when I look at the widest frequency range. Very smooth lines. So I have plotted those data points, and the ruler now is on the phase noise, and I move it to the amplitude noise here. So the hybrids, the noise from them is not interfering with my measurements, but the margin is small. Well, it's both of the hybrids, and I don't know if one is better than the other or if they are similar. That could be a study some other time, but for now this will be enough. The proper way is, of course, to study this in an interferometer, which is partly what I have, but I don't have the balancing tools at the moment. It is also questionable whether this measurement is relevant, because what I'm studying is noise generated in here. What comes here and here may be correlated or independent, and when it comes here, the two signals are summed, and it matters whether the noise here inside is correlated or not when it adds and comes out here. But what is the important thing is for the single hybrid, the one which is sitting here, the noise that this thing adds, whether there is a correlated component in the two outputs. Because noise that this may add that is unrelated, uncorrelated between the outputs will not hurt this measurement. So this study is incomplete, but it shows that there is noise in the hybrids at levels not too far below the levels of the studied object. So this may become important in the future with better oscillators. But there are noise-free hybrids in case necessary.